Have you ever really stopped to think about what holds our world together? At the most basic level, it's not some kind of magic. It is pure chemistry. There are these invisible forces all around us, building the very substances we use every single day, like, say, the salt in your kitchen. Today, we're going to pull back the curtain on the incredible story of attraction that makes all of this possible.
So, let's kick things off with a question about something I guarantee you've seen a million times. Why is it that table salt crystals form these perfect, tiny little cubes? The answer, it turns out, isn't just about the shape. It's actually a clue, a window into a massive, unbelievably organized world hidden inside just one single grain. To get to that answer, here's the game plan. We're going to start with the great electron giveaway, then witness the birth of an ion. After that, we'll see an unbreakable attraction, understand why structure is everything, and finally, we'll learn how to speak the language of chemistry.
Okay, so our story really begins with one simple desire that pretty much every atom has: stability. See, an atom's #1 goal in life is to get a full outer shell of electrons. It's this fundamental drive, this quest, that makes them interact, give away, and take electrons from each other.
And in this little chemical drama, we've got two main characters. On one side, you have your metal atoms. Now, they usually have just 1 or 2 electrons in their outer shell, and honestly, they'd be much happier without them. Then, on the other side, you have the non-metal atoms. Their outer shells are almost full, and they are desperate to find that one last electron to feel complete.
So what do you think happens when these two meet? Well, this is where the action really starts. It's the moment when a simple transfer of an electron creates something totally new, a charged particle. Let's look at the classic example, sodium and chlorine. The sodium atom has this one lonely electron in its outer shell. Chlorine, on the other hand, has 7. It just needs 1 more to have a full set. So in this really elegant transaction, sodium just gives its electron over to chlorine. And boom, both atoms now have what they've always wanted, a full outer shell. But in doing so, they've changed forever. You see, they're not neutral atoms anymore. They've become what we call ions. And an ion is really just an atom that now has an electrical charge because its number of electrons doesn't balance out its number of protons anymore. And there are 2 types, 2 flavors, if you will. The metal atom, our sodium, lost a negative electron, right? So now it has an overall positive charge. We call that a cation. And the nonmetal, chlorine, gained a negative electron, so it now has an overall negative charge. And that's an anion. So just remember, metals make positive cations and nonmetals make negative anions. And what's so cool about this is that it's not random at all. You can actually predict the charge an ion is going to have just by looking at where it is on the periodic table. Elements in group 1, like sodium, they always form a +1 ion. Group 2 elements, they form a +2. And if you zip over to the other side, group 7 elements, like chlorine, always grab an electron to form a -1 ion. It's this beautiful, predictable system. Okay, so we've got our positive cation and our negative anion. Now what? Well, you know what they say, opposites attract. And in the world of ions, that attraction is ridiculously powerful. So powerful, in fact, that it builds something massive out of these tiny little particles. And that powerful force of attraction is the ionic bond. It's not like a string or a little hook connecting them. It's a powerful electrostatic force that's pulling those positive and negative ions together from every single direction. It's one of nature's fundamental forces at work. So, this strong, multi-directional pull is what creates the giant ionic lattice. Think of it as a perfect 3-dimensional repeating pattern of positive and negative ions all packed together. And hey, that brings us right back to our first question. This perfectly regular repeating structure is exactly why salt forms those perfect little cubes. And when we say giant, we really mean it. A single tiny grain of salt can hold about 1.2 quintillion ions. That's a 1.2 with 18 zeros after it. I mean, just let that number sink in. It's absolutely staggering, and they're all locked together in one perfect structure. So why does this microscopic grid matter to us in our big macroscopic world? Well, because this structure is the secret to explaining all the physical properties of these compounds, the stuff we can actually see and measure. For instance, have you ever tried to melt salt on your stove? Yeah, it's not going to work. So why is it so ridiculously hard to melt salt and other ionic compounds?
Well, it all goes back to the lattice. That giant structure has a massive number of ions, and they are all held together by tons of incredibly strong ionic bonds. So if you want to melt it, you have to break every single one of those bonds to get the ions to move. That takes a huge amount of energy, which means you need a very, very high temperature. And the numbers really tell the story here. Sodium chloride melts at a blistering 801 degrees Celsius. But check out magnesium oxide. It's over 2,800 degrees. Why so much higher? Well, magnesium forms a +2 ion and oxygen a -2. That stronger charge creates a way stronger attraction, an ionic bond that needs even more energy to break apart. What about electricity? Right, for something to conduct electricity, you need two things. You need charged particles, and those particles have to be free to move. Now, in a solid chunk of salt, you've got the charged particles, the ions, but they are locked in place. They can't go anywhere. But if you melt it or dissolve it in water, those ions break free from the lattice. Now they can move around, and because they're charged and mobile, they can carry an electric current. So, we've seen how these compounds form and how they act. For our final section, let's learn how to actually write their formulas. It's kind of like learning to speak their language. Okay, here it is. The single most important thing to remember, the golden rule, is that an ionic compound, when it's all put together, is always neutral. The total positive charge from the cations has to perfectly, and I mean perfectly, balance out the total negative charge from the anions. Let's just walk through an example together. How do we figure out the formula for aluminum oxide? Okay, step 1, identify the ions. Aluminum is in group 3, so it forms a 3+ ion. Oxygen is in group 6, so it forms a 2- ion. Right. Now, how do we balance a +3 and a -2 charge? Well, the easiest way is to find the lowest common multiple, which is 6. So we'll need 2 of those aluminum ions to get a total charge of +6. And we'll need 3 of the oxide ions to get a total of -6. +6 and -6 cancel out perfectly, which gives us our final formula, Al2O3. And naming these things is often just as simple. If the compound is made of just 2 elements, like our old friends, sodium and chlorine, the name just ends in "ide," so sodium chloride. If it's got 3 or more elements and one of them is oxygen, the name usually ends in "ate," like in calcium carbonate. See? They're simple rules that tell you exactly what's inside. And there you have it. We've gone on this whole journey, from a simple little electron swap between 2 atoms just looking for some stability, to the creation of charged ions, to this immense, powerful attraction that locks quintillions of them into a perfect solid lattice. That right there is the incredible power of the ionic bond, building the solid, stable world that's all around us. And that leaves us with a final thing to chew on. We've seen how the attraction between charged ions creates these incredibly strong, stable materials. But this is just one type of chemical bond. So, what other kinds of fundamental forces are out there, busy building the rest of the amazing and diverse chemical world that we see every day?